And then we solve problems. Okay, so for any question in this particular exam, it's going to be essentially these two things. Well, I would recommend drawing a free body diagram. We do not say in the exam draw free body diagrams, but I recommend drawing you draw free body diagrams because we might give partial credit for free body diagram even if you got the answer wrong. So once you draw a free body diagram, really the question to ask is, are there conservative forces only? Examples of conservative forces are spring, gravity, and that's about it. So if there are only conservative forces, use T1 plus V1 equals T2 plus V2. This is called a principle of conservation of energy. Else, okay, that is for non so non-conservative forces are friction, external torque, external moment. Use T1 plus U12 equals T2. Okay. And so if you still blank on what to use, then I can tell you that if you use F equals ma, what you learned in the previous, chapter 13 and 17 will always work. Okay, it might be more calculations, but it will always work. So even if you forget what to do, you can quickly try to set up F equals ma and put up the forces. I think we should give you partial credit for that. Don't just put F equals ma, just say how you go about solving the problem. Okay, but for any questions in this exam, if you do use these two principles, you should get the problems. You should be able to solve the problems completely because we've checked the solutions using those two principles. Sometimes it's not possible to use F equals ma to solve the problem because you cannot hand solve the questions. You need to use numerical techniques to do it. So if you have to integrate something which is very complex and you cannot integrate it using a calculator or by the tables you have, then you are in trouble. You will not be able to solve it. That's why I do not recommend using F equals ma, but using these principles. Okay, so I will use this to solve problems. I'm going to assume that you know, but let me just put this down. The formulas for potentials. So potential, this is V, Vg is mg delta H so it's positive when delta H is upwards, it's 0 when delta H is 0 or on the datum, and then equals minus mg delta H when delta H is downwards, right? Similarly for the spring potential, it turns out that it's always half k S minus S0 square, where S is unstretched length, S is the stretched length, and S0 is unstretched length. So I recommend you remember the convention for one of these two, because if you try to do both, then you might get confused. What I mean by that is, if U12 due to gravity is always going to be minus mg delta h, if delta h is down, move down, 0. If delta h is equal to 0 or on the datum, no movement, or equals mg plus delta h, if should be up, is down. And then U12 due to a spring is minus half k s minus s0 square. So what you notice is that the sign convention is reversed for work done. It's negative, it's positive, it's negative here, it's positive there, positive here, negative there. So instead of remembering both of these and getting confused, try to remember only one of them, either this one or this one. You just switch the signs. I like to remember potentials. When you move a mass up, it has ability to do work, so it has a positive potential. And the spring is positive because when you stretch the spring, it has ability to do work, which means that it has a positive potential. That's how I remember it. Okay, so let's use all this and solve a few problems today. Okay, if the unstretched length of the spring is 0.5 meters, then find the total potential at A. Okay, and the total potential at B. Assume datum is at B. So what I forgot to mention is that the particle moves from A to B. Okay, so normally you will not be given a datum, but in this case I have intentionally put a datum and asked you to find the potential, because you cannot find a potential, especially the spring potential, unless you have a datum, right? Okay, so first question is find the potential at A. Okay, as I said, the only two things we need to remember: spring potential and gravity potential. There's gravity here, there's a spring here, so we'll try to write the potential due to spring at A and potential due to gravity, so Vg at A. Okay, so the spring force is half k stretch length minus unstretched length square. The same formula I written down with a positive sign, right? Potential is positive. Since the datum is down there, mg, so the potential is going to be mg times the distance from the datum. The datum is here, so the mass is 2 meters above, so it's 2. And the question is, what's the sign on this? Positive or negative? Positive, right? If you move above the datum is positive, below the datum is negative. Okay, so we need to find, we know what m is, we know what g is, we know what k is. We need to find s and s0. So s0 is what? 0.5. And we need to find s. S is the stretch length. The length of the spring. Right, in this configuration. How can you find the length of the spring? So Pythagoras theorem. So to find s, to 1.5, we need to find this. This is s. That's 2 square plus 1.5 square. So this is So I get 2.5. That's 2.5. So half times 200 times comes out to be 458.86 joules. Okay, so that's the potential at A. We need to find a potential at B. So V B, again, this system has a spring force and a force due to gravity. So Vs, Vg, A, sorry, P and B. So Vs at B is half K, the stretched length minus unstretched length square plus what's the potential due to gravity? It's 0, right? Because the mass is going to end up on the datum at 0. So we just need to find S, because we know S0, this is 0.5. So S is going to be, so what's S? 1.5, because when the mass moves to B, the length of the spring is going to be 1.5. So 1.5. So this is half times 200 times so VB is 100 joules. So something you can expect a question like this in the short answer questions. It will be a partial question. It won't ask you to solve for. In this case, the normal question is, if it's released from A and goes to B, what's the velocity at B? That's the usual question. But you can be asked something like this. Take a question and divide it into half. Anyway, we'll do the next part in the second part in the continuation of this problem. So we need to find the velocity of the collar at B. Okay. So this sort of continuation on the same problem. So if this problem came as a fresh problem and you were supposed to solve this problem, as I said, draw a free body diagram, right? I'll skip that over here, but you should draw a free body diagram for the collar. And then the question is, are there conservative forces or not? So are there conservative forces here, or are there non-conservative forces too? So there's just conservative forces. So if there are only conservative forces, then use T1 plus V1 equals T2 plus V2. So let me just draw the free body diagram just for the sake of it. FBD. So since the spring is stretched, it will apply a force such that it will try to unstretch. So the force is going to be in the direction I've shown there. F spring mg, and since this is sliding on a slider, the slider is applying a force normal, right? And I'm going to assume no friction, so there's no force which is preventing it from moving. But if there was friction, then, well, if there was friction, first of all, you cannot apply principle of conservation of energy, right? Because that's a non-conservative force, so you would apply principle of work done. But since there's no friction, you are fine applying conservation of energy. So let's apply conservation of energy, which states that T1 plus V1 equals T2 plus V2. Okay, we're given here that the collar starts from rest, so the initial kinetic energy is 0. Okay, V1, in order to find V1, we need to find the potential at 1 or at A. This is at A and this is, okay, but we already did that work in the previous part, right? So what we did was we fixed the datum here and we found the potential at A. So I'm going to just use that instead of trying to recompute it. So if you go back, it's 458.86 equals the new kinetic energy, which is half mv square at B, plus the potential, complete potential at B, which was found out previously. So it's 100, right? From here it's 100. Okay, so we have 458.86 minus 100 equals half times mass, which is 3 kilograms times Vp square. So we can solve for Vb. It's 15.5 meters per second. Okay, any questions on this? No questions. Okay. I wish I had not written this. Okay, the spool has a mass of 20 kilograms and radius of gyration of 160 millimeters. If the 15 kg block is released from rest, so starts from rest, determine the velocity of the block when it descends 600 millimeters. So again, the key here is velocity as a function of displacement. So you're going to use either conservation of energy or principle of work and energy, right? The other thing to notice is that you're given the radius of gyration. That's a hint that this is not from chapter 14, but it's from chapter 18, which is the chapter on on rigid bodies. Okay, so when you find the kinetic energy, you have to be mindful about the rotational energy due to inertia. Okay, but the recipe is essentially the same. Draw free body diagram, figure out if there are conservative forces or not, and apply the right principle. So let's follow that recipe which I written on earlier. Let's draw the free body diagram. Okay, here in this case, I would rather draw a free body diagram of the complete system instead of drawing it for individual. So I can draw 3 free body diagrams, right? I can draw it for the pulley, 1 free body diagram, for the mass, the 2nd free body diagram. The 3rd one is for the pulley and the mass as a complete one system. Okay. In this case, I just want to draw it for the complete system because essentially I'm not interested in the tension. If I draw individual free body diagrams, it gives me the tension, and I'm not interested in that. So I'm going to draw a complete free body diagram for the complete system. Okay. So MAG, okay. When I draw the free body diagram of the pulley, since I'll be removing the pin joint that is detaching the pulley from the ground, I need to replace the pin joint with appropriate reaction forces. So there would be a force in the horizontal direction, let me call it HO. There'll be a force in the vertical direction, let me call that VO. And then of course there would be MBG. Okay, so note that in that free body diagram which I just drew, the tension will not appear. Do not write P and do not show an arrow. That will be considered wrong. That's because when you have things, when the tension is an internal force, it will not show up in the free body diagram. The moment you cut this, however, you should show the tension. So do not show the tension in that free body diagram. That's wrong. That's not a right free body diagram. You only write forces which show up as external forces on the free body diagram. Do not draw internal forces. Okay, so now let's think of what principle to apply. Are there conservative forces? Are there any non-conservative forces here? So non-conservative forces are external moment, external force, and then there is friction. There are moment. There's no external moment there. So these looks like they are external forces, right? But these forces essentially don't do any. They are applied to point O, and that point O doesn't move. So they don't really contribute towards the work done. So you can safely assume that those forces are not to be counted against the external forces. So ignoring those, there are no non-conservative forces, no external moments, no external forces, and no friction forces. So no non-conservative forces. So we apply principle of so T1 plus V1 equals T2 plus V2. Okay, so the system starts from rest, so T1 is 0. What's the kinetic energy of the whole system? There is a pulley and then there is a mass. So the pulley rotates about O. So its rotation about fixed axis. So when something rotates about a fixed axis, the inertia is always half I O omega square, right? There is no. So there are two parts to the kinetic energy of a rigid body. There is a part due to rotation, which is half I omega square, and then there's a part due to translation, which is half mvg square. But since this point O doesn't translate, the velocity is 0, so it's only due to the kinetic energy is only due to rotation. And then there is MA, my bad, this should be MP, MAVA square, where A is this. Okay, a particle has only translation energy. It doesn't have rotational energy because we assume that the inertia of a particle is 0. Okay, so that's the expression for the total kinetic energy. We can simplify something. We can find a relation between VA and omega. Since the velocity is that, we can write VA equals omega times the radius. So let's call this R times R. So that is half omega square plus half MA omega R square, which is half IO plus MA R square times omega square. Okay, so finally we need to find a potential. Yeah, we need to choose a datum to find the potential. There are no spring forces. The good news is that we only have to deal with the gravity potential. So, do you have a preference? Where do you want to put the datum? You can put it at A, of course. You can also put it at O. You can also put it. You can put it anywhere, basically. What you want to do, however, is try to find the datum such that one of these will turn out to be 0. So if you put the datum as over here, when it's at rest, then D1 will essentially be 0. Right? Then you have to only find what's the potential when this one descends by 0.6 meters. So let's put the datum at A. So this choice enables us to put V1 equals 0. Now we need to find V2, which is what's the potential due to A dropping down a distance of 0.6 meters. So for that, we know that the potential is MAG times 0.6. What is the sign on that? So if the mass descends by 0.6 meters, what's the potential? Yeah, somebody said negative. That's right. Okay, so let's put everything together. This and this into T1 plus V1 equals T2, which is half IO M AR square omega square minus MAG times 0.6. So 0 equals half. So IO is the mass 20 kgs times the radius of gyration squared, which is 0.16, plus mass of A, which is 15 kilograms, times the radius, which is 0.2 square, times omega square minus MA, which is 15 times 9.81 times 0.6. So the only unknown in that equation is omega. So it's alpha omega to get I think I got 12.5. Okay, I think I might have used 10 over here for gravity. So 12.5. So velocity of A, which is the unknown, is omega times R, which is 12.5 times 0.2, which is 2.5. meters per second. Okay. Any questions on that? Yeah. T2. Yeah, okay. So the question is, how do you find T2? So T2. So T2 is the kinetic energy of the system, of the complete system. Okay. So the complete system consists of two parts: the pulley and the mass. So the pulley is a rigid body. It has two parts to it. It has the part due to rotation, which is half I omega square, and the part due to translation, half mv v0 square. But the pulley is only rotating. It's not translating, so the translation energy is 0, only rotation. That's the first part. The second part is due to a particle. A particle, which is the mass A, can only translate, it cannot rotate. So there's only going to be a part due to translation. So then, once you have this, is there a way in which we can simplify this? Turns out the velocity of A is omega times r. That's just from kinematics, because that pulley doesn't, the string doesn't slip. So velocity is omega times r, and I simplified it to get. Any other questions? So you could potentially do the same problem using principle of work and energy, right? T1 and T2 would be the same as what is given here. U12, the work done. So instead of writing potential of the mass, you would write the work done by the mass. Okay. And you should get the same answer. Okay, so you can totally do this by principle of work done. So I'm going to write that down here. Okay, next question. A small box of mass m is given a speed of square root gr divided by 4 at the top of a smooth half cylinder. Determine the angle theta, so you're going to find theta, at which the box leaves the cylinder. So one thing is clear is that this question is not in the traditional language of this particular two sections. All the questions in the sections have essentially the flavor of find velocity as a function of displacement or displacement as a function of velocity. But this one asks you to find the angle at which the box leaves the cylinder. Okay, so it's worded differently, which makes you feel this is not from this chapter. Okay, what we'll do is we'll try to find what is the condition which will make that particle leave the surface, and then from there we'll see what's the best way to solve this. Whether we can use concepts of this chapter or we can use something else. So when the particle leaves the surface, the only way that will happen is when the normal force on the particle goes to 0. So we need to find an expression for the normal force between the particle and the sphere, which means we have to draw a free body diagram. So let's start off with the free body diagram of the particle So the normal force is always passes through the center of the circle. That's a property of the of a circle, which is normal always passes through the center. Okay. So gravity is there because you can see the velocity is a function of gravity. So I'm going to put gravitational forces. Is there any other forces? So smooth half cylinder, which means there's no friction forces. So I think that's about it. Okay, since we need to set up an equation for n, we need to choose a coordinate system, right? Because we need to write the equation f equals ma in a suitable coordinate frame. For a particle going in a circle, I recommend either r theta or nt. Both of them will work equally well. In general, nt is better here because really, actually, r theta is fine too. I'm just going to use nt. So you could use nt or r theta. So nt coordinate would look like this: n and t, un, and ut. Okay, so we need to write equations of motion only because we need to find set n equals 0 to find a condition which theta is to be found. So set up the equation of motion. This is theta. So F equals ma, and what I'm going to do is I'm only going to write this equation in the normal direction because I need to find an expression for n. So Fn is mass times an. So the force in the normal direction is n, which is acting against un, so it's negative. And then there's mg cosine theta acting in the un direction, so the sign on that is positive, equals mass times the acceleration in the normal direction. This is something which is in the formula sheet, right? The formula is, so assume that this, so let's assume that this is 1 at instance 1, and when it leaves it's instance 2. So I'm going to write this as v2 square divided by the radius, right? This is the acceleration of the particle. So to find, so condition for box to leave the cylinder is the normal force goes to 0, which means mg cosine theta equals mv2 square divided by r. Or in other words, if you have to solve for cosine theta, it's cosine theta equals v2 square divided by r. I dropped gravity, there it comes back. Okay, so g and r are known, right? Because they're given, they're part of the problem. What is unknown is v2. So I need to find an expression for velocity and put it here. In other words, this is one equation with two unknowns, v2 and theta. I cannot solve for both unknowns with one equation, so I need to generate another equation. So what equation am I looking for? I'm trying to look for another expression between v and theta. So this is where this chapter comes in. You're going to find another expression, equation 2, which relates velocity with theta. And the other way to find a relation between velocity and theta is to use either conservation of energy or principle of work done. Okay, so that's the purpose. I'm going to try to use one of the two principles. What should I use? Should I use principle of conservation of energy or principle of work done? Yeah, question? Can you say that again? Yeah, so that this velocity is over here, and you're given the velocity here, right? This is v1. Yeah, so it does not leave the surface at A, because you can see when it is over here, the normal force is mg minus mv1 squared divided by r. It's not 0, so that's not. So we cannot put that here. So we need to still find v2. Okay. So as I said, we would use principle of conservation because v is a function of theta. You have a preference on what you use. There's two options. There's conservation of energy and there's principle of work and energy. So it's conservation, but I can tell you that if you use principle of work done, you'll get the same answer. So let's use the conservation of energy just because that's what we said we're going to use. So conservation of energy. So T1 plus V1 is T2 plus V2. In order to find the potential, we need to fix a datum. So really, you have two options. You can put a datum at A or 1, or you could put a datum at 2. I'm just going to put the datum at 1. So let's put the datum here. Which means that I can now write the kinetic energy at 1, which is only due to the particle translating, half m v1 square, we're given v1. The potential at 1 is 0 because the datum is at 1, half m v2 square, plus we need to find the change in potential due to going from 1 to 2, so delta H. So mg delta H, is it positive or negative sign? The potential is negative. So what's delta H? R minus R cosine theta, right? So I'm going to sub in the values for V1, it's square root GR divided by 4 because it's given here, and that is squared, equals half mv2 square, that's an unknown, mg r minus r cosine theta. Okay, what we can do is, let me write this as 1, this as 2, sub 1 in 2, right? I can take the v2 from 1 and sub it in 2 so that I can now solve this equation in terms of theta. So if I do that, I get half m gr divided by 4 equals half m v2 square is gr cosine theta from 1 minus mg, I'm going to pull that r out, 1 minus cosine theta. So mg r cancels off. I'm left with 1/8 equals 1/2 cosine theta minus 1 plus cosine theta. If I solve for cosine theta, I get 3/4. Or in other words, theta equals cosine inverse 3/4, which is 41.4 degrees. Any questions on that? Okay, so I will see you on Friday. Please come prepared for the class like you would for the exam. I'll have short questions. I'll make you solve the questions, answer using iClicker. So please get your iClickers, and we can go from there. Okay, your exam is on Friday, usual time, same room.